Many are mistaken if they think the Zeroth Law of Thermodynamics is limited to macroscopic contacted temperature measurements. The Zeroth Law is foundational in thermal physics across all scales, from quantum mechanics, atomic interactions and everyday phenomena to cosmic temperature mapping in space science. This law describes the relationship between the temperatures of different objects, enabling us to measure both contacted and remote temperatures, extract energy information, and explore the universe's hidden structure. The law states that if two systems are each in thermal equilibrium with a third, they are also in equilibrium with each other. This transitive relationship allows us to define temperature as a consistent and measurable quantity, independent of the specific materials or methods used. It explains how thermometers function. They reach equilibrium with the object being measured and accurately reflect its temperature. However, the implications of the Zeroth Law extend far beyond simple temperature readings. By enabling precise temperature measurement, it allows us to explore the different phase states of matter and understand their various properties in depth. It is crucial for comprehending how energy flows through matter and how materials respond to that energy. The Zeroth Law quantifies energy, the agent of all transformation, through its thermal effects. Since matter and energy are the building blocks of the universe, this law connects them using the shared concepts of temperature and equilibrium. Additionally, the Zeroth Law enables non-contact temperature sensing. Devices like infrared thermometers and thermal cameras detect the infrared radiation naturally emitted by objects and compare it to a calibrated sensor baseline, simulating thermal equilibrium electronically to estimate the object's temperature. This capability allows for accurate temperature measurements without physical contact, essential in fields like medicine and engineering. In astronomy, the Zeroth Law is the foundation for determining the temperatures of everything from stars and galaxies to black holes, supernovae, and even the faint glow of the cosmic microwave background radiation, all through the thermal radiation they emit. By analyzing the intensity and spectral distribution of emitted thermal radiation across the full range, including infrared, scientists can accurately calculate the temperature of distant celestial bodies. Without this principle, we wouldn't know, for example, that the surface of the Sun is nearly 5,800 Kelvin, that deep space has a temperature of about 2.7 Kelvin, or that exoplanets light years away might have climates similar to Earth's. Remarkably, this same law also demonstrates how we define temperature at the atomic and subatomic scales, where particles obey quantum rules yet still exchange energy in measurable ways. Even in ultra-cold atomic traps or high-energy plasma fields, a signal-based inference of thermal equilibrium allows us to assign temperature to particles too small to observe, whether atoms, ions, or electrons, yet fundamental to everything. That's the true power of the Zeroth Law. It turns thermal equilibrium from a simple idea into a universal diagnostic tool. It enables us to define matter, measure energy, and decode the invisible heat signatures that shape both our quantum world and the cosmos.